Finally, is everybody ready for section 4, Riemann sum and Riemann integral? Let's go. Previously, we had been considering the definite integral as a signed area underneath a certain curve, like this. That made sense when we did have a graph. Well, what if we don't? Or even worse, what if we can't? Yes, there are some situations that a graph is so complicated that it cannot be visualized even theoretically. In that case, we're going to need a fundamentally different approach, and we're going to use a method developed by this gentleman here, Georg Friedrich Bernhard Riemann. Sorry, I must be butchering this pronunciation. He's German, and I don't speak German very well. Anyway, I got this picture from Wikipedia. Let's start with a kind of warming up. Let's start easy, okay? Let's start from a concept of a partition. It goes like this. Given interval, given closed and bounded interval a to b, we define a partition x0, x1, x2 all the way up to xn like this. x0 must be always equal to a, the starting point, and then x1 is strictly bigger, x2 is strictly bigger, and so on, all the way up to xn is equal to b. Let's visualize this. Here's an example. x0 is equal to a, x1, x2, x3, all the way up to xn, which is equal to b. That's a partition. If you have a partition, we can consider things like these. Delta xi, which is defined as xi minus 1, and that basically is a width of each individual interval here. Delta x1 is x1 minus x0, this width. Delta x2 is this width. Delta x3 is this width here, the red one, the biggest, and delta x4, and so on and so forth. Among them, the biggest one we write as delta x without this index I. Here in this particular case, delta x3, the red one, is the biggest. Now, why am I particularly interested in this maximum? That's because later on we're going to take a limit where this delta x goes down to 0. If it does, then everything will have to go down to 0 because the maximum is going down to 0. All delta xi have to go down to 0. And that's why we are so keen on this maximum. Now, one more concept before moving on to the next topic. We say a partition is finer than the other if that partition includes all the points of the previous partition. For example, in this picture, let's make it finer by putting several more points, 2 more points in this red interval, and then 1 more point here, and then create a partition with, let's see, 8 points, all these 5 points, and then 3 more points. And that partition is finer than this one. Now, if I remove 1 point, the x1 over here, for example, and then put 100 more points here, that doesn't make this finer than the previous. The new partition, the finer partition must include all the points here. Okay, so much for partition. And then let's move on to the next topic, Riemann sum. One more thing. The concept of partition does not depend upon the function. It depends upon the interval, and that's it. Okay, now Riemann sum. A given real function defined in a closed and bounded interval a, b, we define a partition R f of xi with respect to the function f and partition xi as this quantity. This quantity, Riemann sum, depends upon the function and the partition. Okay? It depends upon both function and the partition. It can be visualized as follows. Now we took the same partition as before, x0, x1, x2, x3, x4 like this. And each delta xi is the width of the subinterval, so width of each rectangle here. And yi star is a y-coordinate value, so it's a height. So height of this rectangle. So if you multiply these two, what do you get? We get an area of individual rectangle. For example, yi star times delta x1 is the area of this first rectangle here. I'm running my mouse here. When I is equal to 2, I'm going to get the second rectangle. Now, summation, adding them all up, what do I get? I get the sum of all these rectangles. That is a Riemann sum. The width are given by the partition, and the height are given by arbitrarily, anywhere between the minimum and the maximum. Now this program is randomized, so you can truly appreciate this part. Yi star is selected anywhere between the minimum and maximum arbitrarily. Let's run it again. Each time I run, the y-coordinate changes, or the height of the rectangles change. Width do not change because I'm keeping the same partition. Now here, I'm particularly lucky this time. First three rectangles are pretty close to the maximum. So this yi values are selected pretty close to the maximum for first three, and this one is a bit different. And as you can see, for each of those pretty close to the maximum, we'll get overestimation of the area. And then if this yi value is pretty close to minimum, then of course we are going to get underestimation of the area. So this yi value is basically bounded by overestimation and underestimation. And sum of all those rectangles put together is a Riemann sum. Now this visualization helps you understand this concept, but as far as the quantity itself is concerned, this expression stands alone. You see, they do not depend upon picture. This is called Riemann sum. Now before moving on, let me make one point here, because I made a bit of a deviation from the expression our textbook author was using, because I didn't really like our textbook author's approach very much. It was incomplete. 2 points. Number one, our textbook author confined himself only to a case where the widths are all the same. We don't have to have it. We may have different widths. Consequently, we have much worse approximation. Now, if you're making a good approximation, then we have to consider best possible situation. But if you want to define something, best possible situation is not very good. The worst possible situation is the way to go. Because just like Murphy's law, everything that can go bad will go bad in mathematics. So how do you capture everything? You have to capture the worst possible situation and go from there. And then everything is captured in between. Did I mention that overestimation, kind of like this, and then underestimation? Those are worst possible cases, two worst possible cases. Too much higher, too much lower, and everything is in between. And even the worst possible situations behave well. In that case, everything will behave well. And that's one reason I deviated away from our textbook author. I took delta xi, the width of the partition, arbitrarily, not uniformly. Next, another issue is even harder to understand. No, excuse me, not this one. Okay, here. Our textbook author uses this kind of expression as a Riemann sum. Instead of y, uses f of x star. And this is okay when your function is continuous. Look at these green rectangles here, and then each y-coordinate value there is associated to appropriate function value of a certain x-coded value here, here, and there respectively. Even if I run this program again, the same thing here. This y-coordinate corresponds to the function value of this x-coordinate. This y-coordinate here corresponds to the function value of that x-coordinate, and so on. So this is okay, as long as we have continuity. Now let's look at the red rectangle here. No association here. This y-coordinate value, which is selected between the maximum and minimum, yeah, but it does not cross the graph here. Consequently, there is no xi or x2 star associated to this y-coordinate value here. In short, this expression is valid for continuous function. This one more general. Our textbook author does not go beyond continuity, so he does it this way, but I want to make it more precise, and that's why I'm doing it this way. Y is height, delta x is width, and height is selected anywhere between the minimum and the maximum, and then randomized, so I'm gonna get all kind of different types of Riemann sums even when I have the same partition. Now if I change the partitions again, in that case I'm gonna get really diverse quantities. So these Riemann sums are really diverse quantities here. So much for Riemann sums. Now in the next video we're going to talk about how to deal with Riemann sums and partitions together and create a Riemann integral. But before that, just a little bit of review again. Earlier on we talked about a partition. Partition does not depend upon function. It depends only upon an interval. And we get it by x0 equals to the starting point, xn equals to the end point, and then a bunch of points in between. There could be hundreds, maybe thousands of points. But in any case, can be visualized kind of like this. Delta xi is the width of each individual partition, here, each individual subinterval. Delta x without index is the maximum. If this goes down to 0, everything goes down to 0. Next, we talked about Riemann sum. Width times height. So this is the area of the rectangle, and add them together. We have the sum of all those rectangles, as visualized kind of like this.